right, in section 6.1, we're looking more at areas under curves, or here, areas trapped between curves. And we're going to employ all the same techniques as we did in chapter 5, in the sense that, okay, if I want to find the area between the pink parabola and the blue line here, with the line is really a curve also, I already know how to find the area under the parabola. If we extend this down, I know how to find this area with rectangles. Go back to a pen. I'm looking at rectangles that are up and down like this. I'm going to have this width delta x, and this height f of x. Well, now if I want to find just the area that was already shaded blue there, I want to subtract off the area of this triangle, which we can also find with integration. Little rectangles like this that go up to the height of the blue line. Well, in between here, here's another rectangle for the triangle. If all I want is the original blue shaded area, then I'm interested in the rectangle in the middle. This rectangle, the one that goes from a height, let's say this curve is f of x up here, and the y equals x curve is g of x. I want to know the one that goes, the difference between f of x and g of x, which is the difference between is a subtraction, right? So the area of the shaded region is, still we're going from x equals 0 to x equals 4. 0 to 4 are my bounds of integration. And I want to do the area under f of x minus g of x dx. Or written out more explicitly, f of x, this is 5x minus x squared, and g of x is just y equals x dx. And that's going to give me the area of the blue region. Now let me clear up some of this trash over here. Get rid of a lot of stuff. Clean it up, clean it up, clean it up. One of the essential pieces when you're writing up your homework assignments for this is you always want to show what the representative rectangle is. And it doesn't have to be perfect, but I want you to show that it goes from this function down here, this g of x function, to the function up here, the f of x function, so you can see where the top and bottom of it are. And I also want you to in particular show that this is an up and down rectangle, not a side to side rectangle, that I'm slicing these up into slices that are delta x wide and integrating with respect to x. Because in other problems in this section, we're going to be turning this on its side. So let's call this problem 1b, where the functions are almost the same. Instead of y equals f of x, now I'm going to do x equals f of y. So this is 5y minus y squared. And then the other function, instead of y equals x, I have x equals y. And this is g of y, so that one's called f and one's called g still. And if you think about this is just the same picture, but on its side, if I want to find the area between the two curves again, this blue shaded area, then I want to use, well, this really the same rectangles I did over there, but now those rectangles are going to be turned on their side. The whole picture is turned on its side. And so now the width of this rectangle is delta y instead of delta x, and over here this height is f of y, and this height is g of y, and the area is the integral of f of y minus g of y dy. We're integrating with respect to y, And what that means in the picture geometrically is that our rectangles are turned on their sides. We have a bunch of rectangles, but you just need to draw one of them in for me. All right, so how do we actually solve this? This is the integral from 0 to 4 here. F of y is 5y minus y squared. G of y is just y. This is actually a very easy integral to solve. It's just a matter of getting the picture set up right. So negative y squared plus 4y dy. This is just a polynomial, so I get negative, raise the power by 1, divide by the new power, raise the power by 1, divide by the new power, and then evaluate this from 0 to 4. I can plug in numbers. Plugging in 4, I get negative 4 cubed is 64 over 3, and then 4 squared is 16 times 4, 64 over 2. If I want to get a common denominator here and solve it, I ultimately wind up with 32 over 3. Now you might be thinking, what if I didn't remember to set this problem up this way? What if I didn't remember to integrate with respect to y and tried to do it the usual way with rectangles that went up and down like this? Well, these rectangles at the beginning are all fine and good. You're still going, in this case, from the function g of y down to f of y, g of y to f of y, g of y to f of y. But notice when you get over here, you've got rectangles that have the same function bounding their top and their bottom. So in the integral over here, you're really like subtracting one function from itself, and that's not going to work without some clever tricks. Now, it is possible to work this with respect to x with these red rectangles, but you'll have to split it up into two separate integrals and treat this part over here separately, where you split the function into the top part of the parabola and the bottom part of the parabola, and that's just way more work than you want to mess with. And so I'm going to encourage you to really look at your problem first in terms of what's the smartest way to arrange the rectangles here, and then tackle the integration. And notice, just because I have y's in my integral in this step, this is actually the exact same thing as integrating this integral up here with x's in it. It doesn't matter what your letter is in terms of the way that you integrate. It matters a lot, though, in terms of the geometry, what you're picturing. So always, always, always draw in this representative rectangle as you're working through a problem. Thanks, I hope that helped.